With all of these preparations in place, we can look towards laying concrete for the actual dam. As stated previously, the amount of concrete to be placed is absolutely astronomical. Let's have a look at some of the components needed to make this unprecedented undertaking possible. For the titanic amount of concrete needed, it makes sense to prepare and mix the concrete on site. Further upstream of our dam site, there's the low-level mixing plant, with a railway and cars for transporting concrete downstream. This plant supplied concrete for diversion tunnels as well. Another concrete mixing plant is located on the Nevada Canyon rim, called the high-level mixing plant. The gravel, rock, sand, and other particulate or aggregate material needed to make concrete is taken from surrounding areas. A few miles upstream and into a flatter area called Hemingway Wash, there's the aggregate classification plant. This plant sorts different material into predefined sizes and piles, again from sand to gravel and so on, in their respective storage mounds. Nearby rail lines cart materials to mixing plants in the canyon. There's also a nearby water clarification tank used for removing particles from water, up on the side of a rise. All of these will later be underwater, in some cases hundreds of feet, when the reservoir of Lake Mead fills. Let's fly back to our Black Canyon worksite. To make some sense of further tools and equipment, I've shown a unit or block of concrete for the dam in its place at the riverbed. More on these blocks in a moment. Our human model gives a size perspective. At this point, we've got a pretty good idea how precipitous and rugged the canyon is. With this block and its dramatic locale in mind, let's continue looking at equipment that makes placing concrete in such a severe place possible. We'll head back up to the canyon rim. While there were roads and tunnels made from the rim down to the canyon floor, the work of transporting and dropping concrete at precise locations is handled from high above, with cableways that span canyon walls. The heaviest capacity cableway, which is still in operation today, is the 150-ton cableway, located across the downstream face of the dam. A hoist house behind the tower holds huge electric motors to operate the cableway. The carriage travels along its cable track, with pulleys or sheaves and separate cables to lower equipment and platforms attached to the carriage. Much of the heavy machinery we've seen up to this point was lowered into the canyon by cableway. There are historical photos of hulking trucks suspended way up in the air, with the driver seated at the wheel, dangling far above the canyon floor. To give an idea of capacity, this 150-ton lift could transport the weight equivalent of something like 70-plus modern light pickup trucks in a single load, though of course the actual dimensions of such a load would be impractical. That said, the massive steel structures we've seen and will see do make use of this incredible carrying capacity. Along with this 150-ton principal cableway, there are at least 8 other temporary cableways installed, which were later removed when no longer needed. These are mobile cableways on tracks, with huge wheeled hoist houses at either side that advance together. This cableway, for example, makes a span of no less than 2,575 feet from rim to rim, and can travel over a comprehensive area that includes much of the dam, intake towers, and spillways. Remaining cableways cover other strategic construction areas like the power station, upstream cofferdam, and so on. Some are for equipment, others are passenger cableways for lowering workers into the canyon, and more. All might be operating simultaneously at any time, for a dense web of cable hoists slung high above the canyon floor, and a steady flow of workers and equipment to and from the site. To support these cableways, and because our wedge-shaped dam needs much more concrete placed at its wide foundation, there's a lifting device called a derrick. About halfway up the canyon wall, with its base at elevation 930 feet above sea level, or about 425 feet from the canyon floor. A derrick is different from a crane in that it has a tall mast structure and a moving boom that's generally a fixed length, with cables that extend from the mast to work the boom as the base rotates. This is a stiff-legged derrick with rigid supporting legs to brace the mast. This particular derrick was removed once dam progress made it irrelevant. Now, let's head back to our single block in progress and place some concrete. This load comes from the high-level mixing plant by cableway in an 8 cubic yard bucket. The bucket is 6 feet in diameter and 8 feet deep. The swinging doors at the bottom will only release if a worker operates the latch mechanism, or by weight against the bottom doors as the bucket touches down. Doors swing open and the concrete batch dumps into a pile as workers shovel it smoothly across the desired area. Concrete forms at the sides are made of steel plates with supporting timber structures. The side forms have vertical corrugations called keyways to lock these blocks in with neighboring blocks and prevent excess movement. The front and rear forms have horizontal corrugations for the same reason. Though this particular block's upstream face is part of the dam exterior, so the custom form has a predefined slant and a smooth surface. Horizontal keyways are formed at the surface as well. The block you see here is the basic unit of construction for the rest of the dam. Let's bring in a few more of these blocks in their proper rows. The first bucket of concrete was placed on June 6, 1933. A month or so later, this is what we see on the canyon floor. Notice the wooden cylinder form sticking out of a block. This is a section of an internal passageway inside the dam, of which there are many, called galleries, for inspection, grouting, drainage, and more. The network of internal galleries will feature more as we progress through dam construction. Returning back to our demonstration block, the forms at the sides are 5 feet tall, and concrete is poured over the area of a block in one 5-foot tall section or lift at a time. This one lift will require something like 100 of these 8-yard buckets to fill. What's even more incredible is that steady progress was made, with all blocks together rising an average 30 feet per month over the course of the build. A minimum of 72 hours must pass between lifts, and no more than 7 consecutive lifts can be placed on a block in 30 days. This is due to the time concrete requires to properly harden and cure. Our block becomes a huge interlocking vertical column as construction progresses upwards. If I advance the timeline some, you can see that circumferential joints side to side and radial joints from front to back are designed such that these columns nest together and resist and distribute pressure from the upstream reservoir side of the dam, ideally across the arched structure. There are many reasons for laying concrete in lifts and separate interlocking columns. One major consideration is how concrete behaves as it expands and contracts, with the dizzying collection of factors acting upon it, like outside temperature, moisture, reservoir water pressure, and so on. Like the horizontal lines in a sidewalk that provide a controlled place for cracking as the concrete expands and contracts, these columns allow movement throughout the dam in smaller sections to make it more flexible in a way, and therefore more resistant to catastrophic or unpredictable cracks that could threaten its integrity. Engineers learned through failure where previous huge concrete dams did crack and come apart under load.